Fractals are shapes that possess a property known as self-similarity, meaning that they contain smaller and smaller copies of themselves. They can be described using an algorithm, a set of rules to generate the fractal. Each application of algorithm or function, and using the output as the input for the next application, is called an iteration. Each iteration produces more and more copies that are similar, but not necessarily identical to the whole shape. Fractals are unique because they are non-differentiable. They cannot be measured like normal shapes or functions. Each time fractals are magnified, the pattern reappears, making it impossible to measure them with conventional means. The following image is an example of self-similarity. The original pattern of this triangle is repeating within its interior. If you zoom further into the image, it will continue to repeat itself. But how do fractals fit our mathematical world? New York and New Jersey, as well as the rest of the East Coast, were recently affected through the destruction of Hurricane Sandy. Earth scientists have been able to predict natural hazards by understanding the use of fractals in nature. Fractals can allow scientists to analyze scales embedded in patterns of chaos. Because fractals are self-similar, we can apply this concept to recurring natural disasters. Previously, scientists had used statistical analysis in order to estimate natural disasters. However, fractals have proven to be more accurate and conclusive because they provide the size, frequency, and date of the disaster. Fractals are not only beneficial in saving human lives and preventing major casualties due to Mother Nature, they are also present in our reproductive rate and capacity. Fractal geometry makes it possible and relatively easy to estimate population growth. The population increases a certain amount of time depending on the growth rate. Mathematically, if we make r the percent growth rate and p the population, the formula will come out to be p equals 1 plus r times p. For example, when r equals 1/2, p increases 50% or simply is 1.5 larger. However, this equation suggests that the population will increase infinitely. Due to shortage of food supply and natural resources, p therefore is limited. So, to limit p, we multiply the growth rate by 1 minus p. This way, as p is getting closer to 1, the growth rate will be multiplied by a number that is getting closer to 0. We now determine that the growth rate should really be r times 1 minus p. If we use it in the above formula, we get p equals 1 plus r times 1 minus p times p. If you plot the values from 1.9 to 3, we derive the fractal form named bifurcation, also known as Feigenbaum fractal. Fractals, though complicated, exist in the simplest forms. There is no need for analysis nor intricate formulas. Fractals allow us to be followed on a snowy day. The flakes of snow are unique and self-similar. The lightning during heavy rainfalls are fractals. The branches of a tree follow the same concept, and the branches resemble the overall appearance of the tree. The fern leaf follows the same pattern. Although they are difficult to grasp, fractals shape our world. So the next time you eat Romanesco, remember that you're eating a fractal and not just the broccoli's cousin.